I think maybe start that. Okay, please sit down. Next session is, start. Are you ready? You ready? Okay. So the next speech is, Martech rendering from Jonathan Kua-san. Okay, welcome. Please welcome Jonathan Kua. Yeah, thank you.
Just checking the line. Okay, good morning, everybody. I am Jonathan Clark, a developer from the Document Foundation. And today I want to give a lightning tour of all of the work a modern software system needs to do in order to actually put text on your screen. It's a little bit of a fun topic. LibreOffice mostly uses libraries to do this work, but understanding these topics better means we understand the trade-offs that our libraries are making for us. So the first thing that we need is some text stored somewhere in a computer's memory. Computers don't understand human language, so instead we've invented a number of encodings to map characters onto numbers, which computers do understand. The most common encoding today is Unicode, and that's what's shown in this example. Now, people can't read those numbers, so we need to convert them into shapes that humans can understand. In order to do that, we need two components. One is a font that contains the actual shapes of the characters we want on the screen, and the other is an algorithm called a shaper. Shapers are very, very complicated. It's much too big of a topic to cover here in any depth. LibreOffice uses the industry standard open source shaper, Harfbuzz. The output of this process is a series of glyph IDs from the font, along with the position that the character should appear on the screen. Now, a glyph inside of a font is a vector graphic. What we mean by that is that they are defined by math to give us a shape that can be scaled up without any loss of detail. Glyphs are defined by an outline. An outline consists of a set of contours, each of which is a chain of line segments and quadratic Bezier splines. And so here is the math for a line segment. If you remember linear interpolation, we have two control points, P0 and P1, and we interpolate between those 2 points using this function that's parameterized over t, where t is a real number from 0 to 1. Quadratic Bezier splines work similarly, but they have 3 control points rather than 2. These contours are directed. So the way they work is that each segment is connected to the next one by the last control point. So the last control point of the first line segment is the first control point of the next quadratic Bezier spline. And by defining the control points in this order, we give a direction to the contour. Now, this is just the glyph outline. We still need to find the actual interior of the glyph. So in order to define that, we need to introduce a new concept for math called a winding number. I'm going to skip the mathematician's definition of winding number. To intuitively understand what this does, it's best to work through an example. So we start with this simple glyph with that outline, and we choose a point somewhere in the plane. We initialize the counter to 0. We cast a ray to the right. Anytime it crosses a contour going up, we add 1 to our count, and anytime it crosses a contour going down, we subtract 1. So in this case, we intersected with a contour going up, so we add 1 to our counter. And then contour going down, so we subtract 1. And our final winding number is 0, which means our point is outside of the glyph. So choosing another point, we work through it again. Contour is moving down, so we subtract 1. Contour is moving up, so we add 1. And then moving down. And finally, we have -1. Because this winding number is non-zero, we say that this point is inside the glyph. You repeat this process for every point in the plane. We fill the glyph solid. Now, computers don't know how to actually draw vector graphics. All of our displays use pixels, so we need to convert our vector graphic to pixels in order to actually draw it. When we convert a vector graphic to pixels, it's called rasterization. And so as a kind of a first attempt at this process, maybe let's repeat our right word ray test, but this time we do it from representative points. Now in this case, let's say that we choose our points that are going to be in the middle of every pixel in our finished image. And then we perform our right word ray test for every one of those points. Now when we're working from simple examples on a screen, humans are very good at eyeballing the solutions to these kinds of problems, but computers actually have to do the math. And so just working from our original equation, we end up with, the math isn't important, but we end up with a quadratic equation we need to solve. And that's expensive. And so if we're solving that equation for every pixel and for every curve in a glyph, that cost adds up very quickly. So a brief aside about performance. Computers are fast today, but they're not as fast as you think. Modern systems involve a lot of clever algorithms and a lot of hard work over decades to achieve the performance that we see today. And responsiveness, performance aside, computation takes energy. Every operation that your computer performs takes joules. And so if we want to have good battery life on our devices or environmentally conscious software, we do need to think about energy. And just to kind of give a little bit of perspective to this, if you think about all the devices in the world that have screens on them that render text, think about how many times a day those devices are performing that right word ray intersection test. It's quadrillions of times, something like that. So it adds up. And something else to consider is that some languages are genuinely more challenging to rasterize than others. These two glyphs are both from the same font, Noto Serif. It's unfortunate, but I think it's uncontroversial that, say, Chinese characters tend to be more complicated than English letters. And that translates to a real cost in rasterization. And it's difficult to do this scientifically because there's no such thing as an equivalent text between languages. But as a rule of thumb, I kind of find that for visually equivalent text, it's around 2 to 3 times more expensive to rasterize CJK text. So we have to optimize, we want to optimize. One thing we can do is just use more efficient math. There are numerical methods for doing these tests better. No real library uses the tests that I showed. But the main thing that we can do is just reduce the work that we're doing. And so we use glyph caches. Rather than rasterizing a glyph every time we draw it on the screen, we rasterize it once, store it somewhere in the computer, usually in memory, and then reuse it anytime we want to draw the same character again. And again, the performance benefit varies depending on the specific language you're using. Some languages have relatively few unique glyphs, unique characters, and benefit a lot from having a glyph cache. In other languages that have usually more characters, more glyphs, we do see a power law distribution in the frequency that glyphs are used in ideographic writing systems, but it's not as good as it is for European languages. These percentages for the time saved, that's rather pessimistic. this is just looking at a single page of text from a novel, from novels. In real life, our glyph caches are big enough that we can store multiple pages at once. So you do get more benefit, but the percentage is not as good as it is for English. All right. Now, currently we have rasterized glyphs, but they don't look very nice. So remember, we used one representative point per pixel, and this leaves us with very jagged looking glyphs. We want them to look nicer. More importantly, we want to be able to represent sub-pixel details on screen. And so it's just important to note that the pixel on your screen isn't a point. It covers an area. And so what we really want for our glyph isn't just one point inside the pixel. Rather, we want to calculate the percentage of the pixel that's covered by the glyph. And a rather ambitious idea is to use an analytical technique to approximate the actual coverage of the glyph over the pixel. I don't believe any practical systems do this, but there are ways that you can approximate it. For instance, by looking at the derivative of the curve and trying to reverse engineer an area from that. Maybe a much easier to understand one is to use supersampling. So instead, you perform the right word array test for a bunch of points for every pixel, and then you take the average, and that gives you the percentage of the pixel that's covered by the glyph. And so one of the main reasons why we want to use anti-aliasing as well is so that we can represent sub-pixel character positions. So this is less relevant for some languages, but in European languages, English, for example, we like to do a lot of minute adjustments of glyph positions in order to make the spaces between letters look more proportionate. And so it's quite subtle, but if you look at the last O and M on the slide, you can see that the space is wider on the top example than it is on the bottom. So in order to do this, we can leverage our anti-aliasing and just apply a very small offset to the control points as we're doing rasterization to bake that subpixel offset into the glyph when we're rasterizing it. And now that we've done that work, we now have another problem again. Inside of English text, a glyph can now have an arbitrary subpixel offset, and our cache doesn't work anymore. So we need to modify our approach to caching glyphs. A rather old idea, which was used in quite a long time ago in some software, is to use a word cache instead of a glyph cache. So you pre-assemble all of the characters inside of a word, rasterize the entire word all at once, and then cache that word. Then anytime you render that word again, you just reuse that from the cache. That is very inefficient. Modern implementations tend to limit the possible subpixel positions of a glyph to some reasonable number. For example, in Skia, they will cache 4 subpixel positions. And unfortunately, as we discussed previously for caching with videographic writing systems, this makes the problem even worse. So now we have, for any arbitrary text, any arbitrary language, possibly 4 times as many glyphs to cache. But anyway, so far we have from the shaper all of our glyph IDs and glyph positions, and from our rasterizer we have those nice looking pre-rendered glyphs that can be delivered quickly to the rest of our software stack. So this would be Harfbuzz and FreeType in LibreOffice. Now there are many ways that we can actually render the text, the assembled text, and send it to the screen. This one is going to be the most familiar for most people if they're in software development. So we use software rendering. What we can do is pre-allocate a large pixel buffer, say a bitmap. And then effectively what we're doing is copying and pasting our pre-rendered glyph images into this larger bitmap. And if you have been doing software development for a while, when you started, this was probably quite simple. You have a GDI that gives you a flat buffer or a hardware frame buffer, and you can draw directly into it. Modern computers, though, have GPUs. This is how you actually get graphics onto a screen today. Your window manager uses the GPU. The contents of your window are uploaded to the GPU as a texture, and it gets rendered on screen just like a video game renders a 3D scene. And so the benefit of this is that GPUs are very fast and very energy efficient at doing what they do. But, of course, this is more complicated. The good news is that this complexity is mostly hidden from you if you are developing this way. But just because the system, the operating system, hides the complexity from you doesn't mean that you can ignore the potential consequences. So this is kind of an idealized picture of what the connection between a GPU and your computer looks like. A GPU is effectively like an entirely separate computer that's embedded into your computer's case. It talks to your CPU over a bus, and it can access RAM directly over the same bus. And so to start with, we have our glyph cache in RAM, and we're ready to start rendering. So the first thing the CPU does is it allocates that buffer and copies the glyphs into that buffer, assembling the image that we want the user to see. And then the CPU sends a command to the GPU, telling it that it needs to copy the image that we assembled into video memory to be sampled as a texture. The nice thing about this is that because the GPU is like a completely separate computer, it knows how to do its own work. So all the CPU needs to do is tell the GPU what to do, and then the GPU is going to do it more or less on its own, asynchronously, which may also be scary if you are a software developer. So anyway, the GPU will go to memory, it'll copy that assembled image into its video memory, and then all we need to do is send one final command to let the GPU know that we're done and that we're only going to use this for texture sampling later on. This enables some internal performance optimizations. So the nice thing about this approach is that it's very easy, especially if you're migrating an existing application. Chances are, if you're using an older program, it already works this way with no code changes required. The major disadvantages, though, anytime you update anything on the screen, you have to update the texture in video memory. And even though the GPUs are very fast, they're on a relatively slow bus. There's a limited bandwidth, limited ability to send information from the CPU to the GPU, from memory to the GPU. When we write an application this way, it's almost like we are streaming video to the graphics card anytime the user interacts with anything on the screen. So if you have a few programs like that all running at once, you can run into performance issues. Now, we don't have that much bus bandwidth, but what we do have is a lot of compute. Modern GPUs are very, very fast at what they do. So here's a second idea. Instead, why don't we render text like it's a 3D scene, just like a 3D game. We say each glyph that we want to put on the screen is a textured polygon. And then instead of having to transfer our finished image, the contents of our window, from RAM to the video memory every time, the final image only ever exists in video memory where it needs to be. We can have video games now that have characters with 120,000 polygons. I think a few hundred polygons for text is pretty reasonable. And so we need to do some setup first. You need a 3D model that describes the glyph topology. So this would be a unit square. And then we need a texture atlas. This contains copies of the glyphs from our glyph cache, along with a table that describes the layout of that texture atlas. Those three pieces are uploaded to the GPU in the exact same manner that the image was transferred in the previous example. And finally, we need to program the GPU. GPUs don't actually know how to draw anything until we tell them what to do. So in this case, we need what's called a vertex program. And what this does is we can use that 3D model that we provided the GPU and change its vertex positions to match where we want the glyph to appear on screen. And then we need a fragment program that can sample from the texture atlas and output the color of the text to the screen. And the great thing about this is that the only time we need to do a large upload to the GPU is when we have new glyphs that we need to render, in which case we need to update our texture atlas. But as long as we're using the same glyphs, we don't have to do any large transfers at all. So to actually render this text, all we need is a very small table. This is 12 numbers. And we get this data more or less directly from HarfBuzz. So we store this table in memory, and then we tell the GPU to do an instance draw using that data. So what that will do is tell the GPU to automatically grab all of these resources we've created, along with our table in memory, and draw all of the text to a frame buffer in a single command. So this is extremely efficient and can be done without any additional CPU involvement. And so the major disadvantage of this approach is that it is far more complicated to actually implement. There are synchronization issues, and in general, GPU programming is considered quite complicated. So you definitely need someone who knows what they're doing to implement this. And this approach doesn't work at all if you don't have a GPU that's reliable, or you don't have good GPU drivers. The major disadvantage is that there is no fallback strategy here. Either this approach will work with your hardware, or you will need to provide a completely separate implementation to handle cases where it won't. But the benefit is that it's really fast and really energy efficient. I think almost any smartphone app that you would use today is going to render text this way. And so I think that this results in a better experience for everyone. But I did want to point out some problems that CJK languages still have. So before we still have the high rasterization cost, but another major issue is still that high cache pressure due to the higher number of glyphs. And this almost gets worse now because we have to upload the glyphs to the GPU. And so now we're using more video memory as well. So a couple of ideas for future investigation. One idea is to use a custom shading algorithm to decompose some of these more complicated characters into smaller glyphs that can be rasterized and cached independently. I don't know if this will work. This is a project for someone with more free time. But I think it could be interesting. If someone does feel ambitious and does want to experiment with this, I would actually recommend starting with a Korean Hangul font, because at least the font already includes isolated JAMO glyphs. So you'd only have to do the shaping work rather than change 20,000 characters in your font. And another potential thing to investigate is to use alternate glyph representations in order to eliminate that subpixel position cache. And so because we're using GPU shaders to actually render our text, we don't need our glyphs to be human recognizable. They can be anything we want. They could be numbers or encoded or compressed in some way. So one concrete attempt to solve something like this is sign distance fields. These were originally used for magnification, but they introduced some unfortunate artifacts, so they round off sharp edges. But if all we want to do is shift them from left to right slightly, maybe we could use something like this to store the glyphs in a way where we don't need to use that subpixel position cache anymore. That's the walkthrough.
Okay, thank you very much. Yeah, so PhD, thank you very much for clapping against me. All right. So, but the time is like we will start 11:50. So at least we have a couple of questions. Do you have any questions? No? No? Okay. Okay. Work.
So my question is, which problem actually do we solving with this? Do we have a performance problem in LibreOffice with CJP or something like this? Or an energy problem? Where's the motivation of doing work there?
Well, I would say that everybody has a performance problem. Mainly, I wanted to discuss more about the compromises that our software stack, the stack that everybody uses to render text, makes, especially when it comes to CJK languages or ideographic writing systems. We've made some unfortunate trade-offs that cause a worse performance for CJK languages compared to others. As well, personally, I think GPUs are neat. And so, in addition to the neatness, they are much more energy efficient. And so if you've ever used a smartphone app, you scroll with your finger and it hasn't scrolled immediately, it's kind of stuttered a bit. Or if you've used, I don't know, if you're just looking at a page of text and your phone gets hot, that application might be using software rasterization.
So we on the call of LibreOffice, we define how efficient it is rendered on different devices.
So in LibreOffice, we rely on libraries to perform our actual last step rendering. So we use either Cairo or Skia. And for Skia, if you use the Vulkan backend, it's doing things the way that I described at the very end. But otherwise, we're doing things slow.